Welcome to this 6G waveform session. I'll give you some background information. If we look at the previous generations of cellular networks, each generation has its own a new waveform, with 5G being only exception, because it still uses OFDM. But 6G provides us the opportunity to employ new waveforms, because the use of the new spectrum, such as terahertz, visible light, and because of the new design paradigm, such as integrated sensing communications and the satellite communications, for which OFDM might not be optimal solution. While OFDM will still be used, this session explores other technologies that could and arguably should be used alongside OFDM as we move beyond 5G. And we have 3 speakers for this session. First, let me briefly introduce myself. My name is Pei Xiao. I'm from University of Surrey. I've been working on different waveforms extensively, including OFDM, ABMC, and today I'm going to present non-orthogonal waveform for 6G. Another speaker is Professor Roni Hadani. He's an inventor and advocate of OTFS, orthogonal time, frequency, and space modulation technique. He's a professor at the University of Austin, Texas, and also the co-founder and chief science officer of Cohere Technologies. And we have Dr. Danny Corpy from Nokia Biolabs. He's a senior specialist in Nokia Biolab, Espoo, Finland. His current research focuses on applying machine learning for wireless communications, especially on physical layer. He's working on building a native foundation for machine learning in beyond 5G and 6G radio networks. So we have 3 presentations today. Roni will present the waveform design in the Doppler and delay domain. I will present non-orthogonal waveform for 6G, and Danny will present AI design waveform for 6G. We have a 40 minutes presentation and followed by 25 minutes panel session. Okay, without further ado, I pass the floor to Roni. Roni, please.
Thank you very much, Pei. Let me share my screen. So everybody can see my screen? All right.
Yes, yes.
Okay, so it's a pleasure to be here. Thank you very much for inviting me for this panel. So I'm going to talk about OTFS, or more precisely about communication in the delayed Doppler domain. First, let me connect it somehow to 6G. So let me spend a few words about 6G. So I'm not sure that anybody is completely clear about what 6G is specifically going to be, how it's going to look like. But there is some level of agreement about some core use cases that 6G will have to account. So let me spell out a few of them. One is extreme mobility, communication under extreme mobility, and the main technical challenge here is performance resilience to high Doppler and fading phenomena. Second is joint communication and sensing, and the challenge here is high resolution radar imaging of the environment. Third is cloud network management, and the main technical challenge here is that you need to predict the channel in order to overcome the additional latency, which comes with moving the processing center away from the tower. And fourth is intelligent network management, or AI. And here the challenge is that you need to learn under non-stationary condition and time constraints. So learning in the context of wireless communication is very different in nature than just machine learning applications in kind of an offline setting. It's a highly online, real-time setting to do machine learning. So it's a challenge. Next, let me say what is OTFS. So OTFS is really a word that captures a paradigm of communication in the delayed Doppler domain, in contrast to the traditional paradigm which casts communication in the time frequency domain. There are three aspects to this paradigm. One is modeling and processing the channel in the delayed Doppler domain, and this gives rise to the delayed Doppler channel representation. Second aspect is multiplexing the information itself in the delayed Doppler domain, which gives rise to a modulation technique or a waveform, which is called OTFS. And the third aspect is that OTFS constitutes a mathematical unification of communication and radar theory, and this gives rise to a framework for doing joint communication and sensing. Just let me mention that to this date, OTFS was the first publication was 3 years ago or 4 years ago. To this day, there are more than 400 scientific publications about OTFS. So there is a community forming around it, and you can read. There are many resources that you can read about it. So let me spend a few words talking about the delayed Doppler channel representation, because this encapsulates the whole motivation for the development. So the wireless channel is not an arbitrary collection of complex numbers. It's underlined by some physics. You have a collection of reflectors. Some of them are moving, some of them are static. You transmit a wave, it propagates, bounce of each of the reflectors, and what you get on the receive side is a superposition of all these reflections. Mathematically speaking, every reflector introduces a combination of time delay and Doppler shift. So you can represent this geometry of reflectors as a two-dimensional impulse response on the delayed Doppler domain. That's what you see on the left. Every tap in this response represents a cluster of reflectors of specific delay and Doppler characteristics. And this is called the delayed Doppler representation of the channel. And the advantageous attributes of this representation are two. It is low dimensional. It represents the channel by the minimum number of parameters, and it is sparse. And second, it is slowly changing. And in this regard, it is easy to learn and predict. Okay? So that's the channel, and now let's discuss how to place the information itself in the delayed Doppler domain. That's a modulation technique, and that's the OTFS modulation. So to this date, we have three basic waveforms. We have TDMA, which carry information over pulses in time. We have OFDM, which carries information over pulses in frequency, which actually, when converted to time by Fourier transform, becomes tones. And we have CDMA, which carries information over things which look like noise, codes. Turns out that these three waveforms are mathematical descendants of a single mother waveform, which, for a lack of a better word, we call it OTFS, which is simultaneously localized in time, like TDMA, localized in frequency like OFDM, and it is spread in some sense like CDMA. So this is how the OTFS waveform looks like. This is the OTFS carrier. This is what carries a single QAM symbol in OTFS. It's a tone sampled over a pulse train. Okay? So this is the analog in OTFS of a tone in OFDM. Okay? You place a single QAM symbol, is carried by this kind of pattern. It's called a pulson. It's a fusion of a tone and a pulse. There is a lot of structure behind this waveform. Locally, notice locally it looks like a pulse, globally it looks like a tone, and it simultaneously behaves like both. And the main characteristic of this pulson is that it remains invariant under the operations of time delay and Doppler shift, which means that when you shift it in time, it preserves its shape. When you shift it in frequency, it preserves its shape. In fact, when you apply Fourier transform to a pulson, you get a pulson. It's self-dual to Fourier transform. So it's very symmetric waveform. And this is beneficial. Being invariant to this operation is beneficial because this means that if you transmit a pulson through an arbitrary environment, the reflections are going to introduce time delay and Doppler shift, but the pulson is invariant under these operations. So if you transmit a pulson on the one side, kind of the environment will operate on it, but the pulson doesn't care about these operations. So you will get something very predictable on the other side. So it's like driving a car with good suspension system. The road might be very bumpy, but the suspension just swallow the bumps and you don't feel it. And this, of course, translates to performance consistency under channel conditions. So we talked about the channel. So now what is the delayed Doppler structure of the pulson? So the statement is that the pulson is the time realization of a localized 2D pulse in the delayed Doppler domain. or more precisely a quasi-periodic 2D pulse, but I'm not going to bother you with the technical definition of quasi-periodicity. What do I mean by that? Well, we have the pulson, that's a waveform in time, and the statement is that it is related to a localized pulse, to a two-dimensional pulse in delayed Doppler, and the way these two patterns are related to one another is by means of a transform, which is called the Zag transform. So you have two ways to think about the pulson. You can think about it as a pulson in time, as a tone sampled over a pulse train, or you can think about it more conceptually as a pulse in delayed Doppler. In the same way that you can think about OFDM as a tone in time or as a pulse in frequency, and the relation is the Fourier transform. So here, the relation is the Zag transform. Now, more specifically, it's interesting to relate these two structures. So the position, the delay coordinate of the pulse in delayed Doppler dictates the displacement in time of the pulse train, and the Doppler position of the pulse in delayed Doppler specifies the frequency of the tone. So if you shift the pulse in delayed Doppler, the pulse train is shifting in time, and then tone is oscillating in different frequencies. Further than that, the width of the pulse in delayed Doppler along delay is inversely proportional to the bandwidth of the pulson, and the width of the pulse along Doppler is inversely proportional to the duration of the pulson. So if you make the pulse narrower and narrower, what you are actually doing, you are extending the bandwidth and duration of your pulson. But in delayed Doppler, it means that you are achieving higher and higher resolution in delay and in Doppler. So it's a kind of a radar intuition which underlies this reciprocal relation. Okay, so we talked about the channel, the delayed Doppler channel. We talked about the delayed Doppler waveform. Now let's try to understand the interaction between the two. So let's first understand the interaction with a pulse and a tone, with TDMA and OFDM, and then contrast it with OTF. So let's say we have an environment comprising of 5 reflectors, 3 are statics, or 3 are statics and 2 are moving, so they have non-zero Doppler, the car and the bus. And let's say that we transmit a TDMA pulse. So it interacts with the reflections, and what you get on the receive side is a cascade of echoes displaced in time according to the characteristics of the reflectors. Now I want you to focus on the second echo, because the second echo is a superposition of 2 reflections which have the same delay, but different Dopplers. And these 2 reflections are going to superimpose on one another. And sometimes this superposition is going to be constructive, and sometimes it's going to be destructive. And as a result, the second echo is going to fluctuate in energy. And this is this creates time selectivity, fading along the time domain. And reciprocally, if you transmit a pulse in frequency, again, it's not localized in time, so it cannot separate reflectors along delay. And what you are going to get on the receive side, again, is a cascade of 3 echoes displaced in frequency according to the Doppler characteristics. And the middle echo is going to fade because it's a superposition of 3 reflections which have the same Doppler. And this is the phenomenon of frequency selectivity. So the main takeaway is that the fading is not an intrinsic property of the channel. The channel doesn't fade, you have reflector. At least not fast fading. But fading is more of an attribute of the interaction of the channel with a specific waveform, and the mechanism behind fading is the non-locality of the waveform along one of the dimensions. This is what creates the fading. You cannot separate the reflections along one dimension, so they superimpose, and as a result, you will get fading. So now let's contrast it with OTFS. What happens when you transmit a pulson? Well, it means that you transmit a pulse in delayed Doppler. It's going to propagate. Of course, you apply the Zag transform, you transmit it, it propagates, interacts with the reflections, then you apply the inverse Zag transform, and what you get is this pattern. You get a cascade of 5 echoes displaced both along delay and along Doppler, and you see that nothing adds up destructively. Okay, and what are the key takeaways from this pattern? Are the following 3 takeaways. This is the most important slide in my presentation. The interaction of the pulson with the channel does not fade because you separate all the reflections from one another, so nothing adds up constructively or destructively. And if you apply the right equalizer, you can accumulate the energy coherently. And in this regard, it's ideal for high mobility because you don't fade on delayed Doppler. Second is the interaction is predictable or stationary. In fact, it doesn't matter where you position the pulse along delayed Doppler, you will get exactly the same interaction. It's a 2-dimensional ISI pattern which is independent of the location. And this means that the interaction is easy to learn. You don't need to learn many parameters. You need to learn only the interference pattern at one position, and you can conclude it at any other position. So you have a lot of sharing of parameters here, and this makes it ideal for machine learning. You can easily learn this interaction. It's very predictable. And third is the interaction separate reflectors, both along delay and along Doppler. And in this regard, it's an ideal for radar imaging or sensing, because what you actually see here, what you can read from this interaction, is the delayed Doppler radar image of the environment. So at the same time of communicating information, you can actually read the geometry of the environment. So you are acting as a radar at the same time as you are acting as a communication transceiver. Finally, let me just say one word. In fact, the pulson is universal. You can view TDMA and OFDM as limiting cases of OTFS in the following sense. If you make the pulses, if you separate the pulses away from one another, what you get in the limit, in the limit, the tone structure disappears and you are left with a single pulse, which is TDMA. And on the other extreme, if you are compressing the pulses against one another, in the limit, the pulse structure disappears and what you get is a continuous tone, which is OFDM. So in fact, you can think about OTFS as a family of modulation techniques which interpolate between TDMA and OFDM. So TDMA and OFDM, in a sense, are just limiting cases of OTFS. So you can view them as particular cases. So you are not losing anything. You are generalizing things that you already know. So it's nice to know that, in fact, TDMA and OFDM are just corner cases of a continuous family of modulation techniques. Finally, let me just summarize the advantages. Advantage in extreme mobility, you don't fade. In addition, I didn't discuss it, but you don't require cyclic prefix. And there is no intercarrier interference phenomena. So all these phenomena which you need to deal with multi-carrier modulation do not exist in the delayed Doppler domain. Second, it's a joint communication and sensing. It's a high resolution. It actually gives you high resolution separation of reflectors, so it acts as a radar. With regard to cloud and intelligent network management, it gives you predictability and stationarity of the input-output relation, which is easy to learn and then work with it. And finally, a topic which I didn't discuss, OTFS is a spread spectrum modulation, and along this thread, it gives you processing gain, and it also can be applied for security communication. You can actually very easily apply codes over OTFS, and in this way come up with all kinds of security protocols. And with this, I will finish. Thank you very much.
Thanks, Ronnie. Yeah, I don't see any questions from audience. So let's move on to the next presentation. We can leave all the questions to the panel session.
Shall I go next, or?
I can do the next.
Yeah, sure.
Okay. Yes, I'm going to present SMA, the non-orthogonal waveform for 6G. What is SMA? It stands for sparse code multiple access. It's a code domain normal and is regarded as strong candidate for future massive type communications. Before our discussion on SMA, we need to talk about its predecessor, low density signature, ODS, which was initially proposed by researchers at the University of Surrey in these two seminal papers. LDS is better explained by comparing it with OFDMA. In OFDMA, each user has dedicated radio resource. Here, 4 users are served by 4 subcarriers. They do not interfere with each other. But suppose we have 6 users to be served by 4 subcarriers. Then inevitably, users have to share subcarriers. We no longer have the luxury to have a dedicated radio resource for each user. In this case, each subcarrier is shared by 3 users. So that's the principle of LDS, and it's simple and straightforward. And this diagram illustrates the connections between users and subcarriers. It's called factor graph or LDS sparse graph. The graph is sparse because we do not have all users connected to all the subcarriers. And the benefit of having such sparsity is to enable low complexity message passing algorithm for maximum likelihood detection. The sparse graph can be equivalently converted to LDS signature matrix. There are 3 important parameters in LDS. The first one is overloading factor. The second one is the multiplexing factor. The third one is spreading factor. That is the number of subcarriers each symbol spreads over. But in this case, the spreading factor dV equals 2. Each symbol is spread over 2 subcarriers. The purpose of spreading is to exploit frequency diversity gain. On the contrary, OFDMA does not have such diversity. Therefore, LDS performs much better than OFDMA. With the knowledge of LDS, it's easy to understand ACMA. In LDS, we have only one constellation. When we perform spreading, for example, the first symbol is spread over the first subcarrier and third subcarrier. These 2 symbols are the same symbol from the same constellation. But in ACMA, we have multiple constellations. Each constellation is a rotated version of the other. When we do spreading, the first symbol is the symbol from the blue constellation, but the second symbol is a symbol from the red constellation. The purpose of having multiple constellations and the constellation rotation is to exploit the so-called constellation shaping gain. The comparison, we can see that the shaping gain is very significant. It's well over 1 dB. That's the main difference between LDS and ACMA. There are 2 design challenges we're going to talk about today. The first one is how to optimize ACMA codebooks for performance improvement. And the second issue is how to reduce decoding complexity. First, let's look at how to improve performance. It's well known that the channel capacity CC is greater than signal set capacity CS, which in turn is greater than BICM capacity CB. CS is only achievable with coding modulations, CM, such as multi-level coding or Travis coding modulation. But existing CM techniques are too complex to be implemented in practice. The existing ACMA systems only achieve CB because they are designed under the bit interleaved coding modulation structure. Now the question is, how can we design a CM-based ACMA to achieve signal set capacity CS? That is possible by considering the joint design of ACMA and LDPC codes. We know LDPC has been adopted in 5G new radio standards for data channels, and LDS is also based on sparse graph, and so is LDS or ACMA. And we tend to believe that these 2 sparse graphs can be merged into one single joined sparse graph. And that leads to the design of CM-based ACMA. There are several advantages by CM-based SMA. First, it has better performance than this disjoint approach because CS is greater than CB. We achieve signal set capacity rather than BICM capacity. Secondly, it also results in lower detection and decoding complexity because we can perform LDPC decoding and multi-user detection simultaneously based on the joint graph. And also, the processing latency is reduced due to the joint decoding and the multi-user detection. So the benefit is really multifold. We have an improved performance and reduced processing latency and complexity. Based on our theoretical analysis, we know that the performance of SMA is largely dictated by the diversity order. The relationship between the beta rate and the diversity order is exponential, meaning that a small increase in diversity order will result in dramatic improvement in BR performance. This motivated us to improve the performance of SMA systems by enhancing the diversity. The most straightforward solution is to increase the spreading factor dV. Instead of spreading each symbol over 2 subcarriers, we can spread it over 3 subcarriers. To this end, we need to have a 3-dimensional constellation instead of 2. And this 3-dimensional approach gives us a lot of performance gain. Another way to improve diversity is by frequency hopping. In conventional SMA, we transmit code words over consecutive time slots. If the code word is in deep fade, it will always be in deep fade. The signal cannot be decoded. To enhance diversity, we scrambled code words across all the subcarriers. If one subcarrier is in deep fade, others might not. The code word can be decoded successfully. This is called frequency hopping SMA. It performs much better than the conventional SMA due to the diversity gain. The frequency hopping SMA does not change the overall structure of SMA system. We just need to insert the frequency hopping block between the SMA encoder and the OFDM modulator. There are some other ways of improving the performance. For example, we can use delayed bit interleaved strategy to effectively increase the interleaving depth. In this way, we have enhanced diversity, resulting in much improved performance. In SMA, the shaping gain is vitally important, but the conventional SMA codebooks are based on QAM modulation, which does not give us much flexibility for optimization. And we replaced QAM with golden angle modulation, which gives more degrees of freedom for constellation shaping, resulting in much improved performance. Unlike the power domain normal, SMA usually does not rely on power imbalance. But power imbalance can actually further improve performance, as we can observe from this comparison. The next issue is how to reduce complexity, which is a bottleneck problem for SMA. The complexity mainly comes from the message passing algorithm, MPA. It has complexity in the order of m to the power of DC. M is modulation order, TC is the multiplexing gain, multiplexing factor. That's the number of users multiplexed on one subcarrier. Obviously, a straightforward approach to reduce complexity is to reduce modulation order n by utilizing the fact that SMA employs multi-dimensional constellation. Let me use this simple example to illustrate this idea. We know from this tracked graph that the symbol from the first user is spread over the first subcarrier, second subcarrier. And we use the blue constellation for first subcarrier, the red constellation for the second subcarrier. In the blue constellation, we deliberately let symbol S2 overlap with symbol S3 in order to reduce the modulation order, to remove the number of constellation points. At first glance, it appears to be a bad idea because S2 and S3 cannot be separated. The Euclidean distance is 0. But the fact is, they are very well separated in the red constellation. Therefore, the code word can still be decoded successfully. And in this way, we effectively reduce the modulation order and leading to significant complexity reduction in the decoding. We achieve 97% reduction compared to the existing SMA codebook design. And this complexity reduction is achieved without sacrificing the BR performance. Another approach to complexity reduction is to replace MPA, message passing algorithm, with expectation propagation algorithm, EPA. EPA has linear complexity rather than the exponential complexity. And the principle is to pass the message in the form of mean value and variance instead of log-likelihood ratios. This significantly reduces decoding complexity. We can see in large-scale SMA systems, the complexity reduction is 3 orders of magnitude, from 10 to the power 8 to 10 to the power 5. Compared to MPA, EPA does not have any performance loss in AWGN channel and acceptable performance loss in relay fitting channel, and the performance loss is not negligible if we use strong channel codes with low code rates. So we not only conduct theoretical research on SMA, we also prototyped our solution. And our experiments demonstrated 300 more connectivity with SMA compared to SC FDMA solution. Now that brings an end to my presentation. Okay, I pass the floor to Danny.
Yeah, thank you. Let me share my screen as well. Yeah, so maybe you can still confirm that you can see the slides there.
Yes.
Yeah,
please
actually.
the first screen, yes, that's perfect.
All right. Yeah, so I have a few slides about another way to approach waveforms in 6G, and in particular, basically how to possibly learn these waveforms using ML. I will start off with this kind of a more general view, how we see the roadmap towards 6G, and especially towards these AI native air interfaces in 6G. So the first point is First point is basically looking at this ML type approaches as more like an algorithm enhancement tool. And this is now something that we are already doing in 5G. So we are already using ML to improve the performance of these individual functional elements inside the radios in the physical layer. So we can, for example, use ML to enhance the channel estimation performance. And then we can see certain performance gains, which we can measure in terms of lower mean squared error for channel estimate. And then this will have a certain improvement for the overall link throughput. But basically, this is, of course, quite limited what we can do with such an optimization approach. So there, the second step is kind of trying to push this a little bit further, where we are using ML to actually jointly optimize like a bigger parts of the system. So now using the example of this figure, so we can basically kind of try to learn, for example, the whole receiver using a big deep neural network, and then we don't enforce any constraints on how the processing is being learned. So we can just feed in the received signal and then basically obtain the information bits from the output of the model, and we don't really care what is happening inside the deep neural network. So this is a kind of a step towards an unexplainable AI, but the benefit is that we can see much more significant performance gains because we are now jointly optimizing the processing. But then, since we are talking about 6G today, so there, one way to approach like the application of machine learning in radio systems is actually to allow these deep neural networks to also learn to design parts of the physical layer. And what this means in practice is that we actually now introduce certain ML elements to the transmitter side. So this means that we are, in a way, allowing the system to optimize the waveforms and jointly learn the receiver processing for detecting the information that is modulated onto this learned waveform. So this means that we are now kind of end-to-end optimizing the physical layer. So we are learning what we need to do on the transmitter side, and then we are learning together jointly with that how to actually do the processing on the receiver side. And this is one way to look at this like a fully AI native air interface. And of course, this doesn't mean that we would learn everything from scratch without any structure, like underlying structure. For example, we saw an interesting presentation about the OTFS given by Ronnie. So there, one possible option would be that we would have certain like OTFS type waveform, and then we are learning some elements of that waveform, and then we are learning the receiver for detecting the information modulated on the OTFS waveform, and this way basically improve the performance by using deep learning. And yeah, a little bit discussion about the possible benefits, which is of course kind of the key point here. You know, we shouldn't just use ML for the sake of ML, but we also need to have a clear idea of what kind of benefits we can expect to obtain. I have already discussed some of these, but of course the most important thing is higher performance. So we can expect to have basically to have some tangible benefits in terms of the performance gains when we are applying these ML type approaches. And also another important thing is sustainability. And when we are looking at this kind of type of hardware that we can use for doing ML inference, so we can see, especially in the future, when these like analog processing chips will be implemented, so we can see quite massive efficiency gains there. So we can calculate the huge number, we can execute a huge number of operations with much lower power consumption than today, and this way we can do the basically the kind of the running of the algorithm with much less power, which will reduce the overall energy consumption of the networks. And also related to the hardware aspects, so flexibility is one important benefit. Because the nice thing about neural networks is that they will actually do the inference using very simple basic operations. So it's very homogeneous in that regard. But we are just repeating the same simple operations, the same simple layers, like for example convolutional layers, over and over again to achieve the desired result. And this is possible to do with a very simple hardware, which is the same regardless of what the deep neural network has been trained to do. So that means that when we want to update something, we just need to learn new weights for the model, but we can still deploy that in the same hardware, as long as the hardware has enough computational elements to execute or do the inference for the deep neural network. And then lastly, there is also potential for reduced algorithm design effort. Although, well, I have now myself been working on this topic for a few years, and I don't know if I believe in this anymore. So it's still a lot of design effort to achieve the performance you need from these deep neural networks. So it's not just plugging in some model and then hoping for the best, but it will actually involve still a considerable amount of human intelligence and design engineering. Yeah, and then kind of to give you some more concrete ideas, what this could look like a fully AI native air interface. So I was already mentioning this end-to-end training. So this is now one example of how we can optimize both the transmitter and the receiver without learning everything from scratch. So here you can see that we still have an OFDM transmitter, which is now used as the basic waveform, but then we are optimizing this waveform with a couple of elements. So first of all, if I just get the pointer to make it a little bit easier. So first of all, we are learning the constellation shape. So this is in a way replacing the QAM constellation that we are using in 5G, for instance. So now instead of that, we are learning this kind of the mapping from the bits or the bits from the so-called symbols, which are essentially just like 2D, in a way 2D representation of these symbols on the complex plane. And then in addition to that, we also have a small convolutional neural network on the transmitter side. And the reason for that is that we want to also make this waveform more resilient towards the nonlinear distortion caused by the PA. So this is now in a way adjusting the PAPR and other properties of the time domain waveform to make it more suitable for the distortion produced by the PA, in order to kind of result in lower emissions, to make sure that we are still fulfilling the emission masks in the standards, and then also to make it possible to be detected more accurately on the receiver side. So now, in addition to the transmitter side, we are also jointly learning the receiver, which is here we refer to it as deep RX. So you can think of it as a deep convolutional neural network. And the key thing here is that we learn all of these together. So you can see this arrow going all the way from the receiver output to the transmitter input. So this is basically now treated as an autoencoder. And what this means is that we try to extract the original message from the output of the receiver. And in practice, we can do this with supervised learning, as long as we have differentiable models of all of these elements in the whole transmitter receiver chain. So we need to have a differentiable transmitter, and then a differentiable channel model, and then a differentiable receiver. And this allows us to do the backpropagation through the whole chain to obtain the updates for the weights based on the loss function, and that way to optimize all of these learned elements. And of course, these elements that are not being learned, like of course the PA model, the channel, the OFDM transmitter, So those are in a way just implemented as fixed layers in the model. And then these highlighted parts here, so those are then the ones that are being learned with the backpropagation and optimized based on the loss function. And this way we can arrive with quite a few different waveforms depending on the training data, depending on the channel models and the the PA profile. So this will always optimize itself based on the prevailing circumstances. Yeah, and then a couple of performance results to give you an idea of what kind of performance gains we can expect to obtain. So now this is showing an example of a learned constellation. You can see that it's not resembling the QAM constellation anymore, so it's quite different. And the reason for this, which I actually didn't yet explain, is that we don't allow this learned waveform to include any channel estimation pilots. So it's all of the resource elements of the OFDM waveform. All of them are just containing transmit data. So this means that the system is actually forced to learn data-aided blind detection, and this it can do by learning a certain type of a constellation shape. Basically, the main requirement for the constellation shape is that it's quite asymmetric, so that the receiver can, in a way, correct for the distortions caused by the channel. So all of the phase and amplitude response of the channel, so that it can correct for those in a blind manner. And of course, the good thing is that this will improve the spectral efficiency, because we can now use all of the available resource elements for data transmission. And we can also see, when we look at the bit error rate performance, that now even the bit error rate is quite competitive. This is mainly due to the fact that we have a nonlinear PA there. So this will learn to deal with that quite efficiently. And these baselines are just linear, based on linear receivers utilizing the CPU OFDM waveform. So of course they are not kind of that capable of dealing with the nonlinearities as the learned receiver and the learned waveform. But we can see ACLR gains there. So we can see that we can improve the ACLR by including the CNN on the transmitter side. Yeah, and we can certainly achieve very accurate detection on the receiver side, even though the waveform didn't include any pilots. So it will learn to kind of work around that by learning the constellation shape and learning to deal with the distortion produced by the PA and also the distortion of the channel. Yeah, but that's all the material I had. So I hope this was enough of an intro to the possibilities of machine learning for 6G. And yeah, I guess now it's time for the questions.
Many thanks, Danny. There's actually a question from audience. So which part of physical layer is your machine learning design involved?
Yeah. Yeah. So shall I answer the question now?
Yeah,
right away?
please.
Yeah. All right. Yeah, that's a good question. So I think this is maybe the best figure to use for that. So in this particular exercise, we are basically learning the link between the channel encoder and the channel decoder. So in 5G, this is either LDPC or polar coding. So basically, this is now kind of operating on the encoded bit sequence, and then finally the learned receiver will output the soft bits or the log likelihood ratios, which will then be fed to the channel decoder. So that is the kind of the part that we are dealing with here.
Okay, thanks, Danny. Any more questions from audience? So if not, let's move on to the panel session. Okay, first I have one general question for panel members. Apart from OFDM, do we expect new waveforms in 6G, considering the use of new spectrum like terahertz visible light, a new design paradigm like integrated sensing and communications, as well as satellite communications?
I believe so. I believe that, again, this is a belief, of course, it's not a declaration, but my perception of 6G is of a multi-waveform standard. So it will be an envelope that will allow the freedom to use for specific use cases waveforms which are optimized for this use case. And in this regard, there will be no 7G. 6G will be general, because all these transitions from a G to a G, I think the communication industry is becoming sophisticated enough to come up with a universal G to a larger extent than in the past. And it will be a multi-waveform standard, perhaps.
Yeah. Yeah, I also think OTFS is very suitable for integrated sensing and communication, as well as
OTFS, for example, is very suitable. Let me be specific. OTFS is very suitable for communication and sensing. It's actually an army-graded radar waveform. You can actually sense your heartbeats if you design the OTFS parameters appropriately. And it's very well suited for mobility. But I wouldn't, take a tank to the supermarket. I wouldn't use OTFS for simple Wi-Fi or static scenarios. You can use multi-carrier waveforms, very good. You will not see a big performance gap. So you need to use OTFS where it is needed, and not for every use.
Yeah, very much agree with that. So yeah, I think the idea that you mentioned, that there are like several possibilities for the waveforms, and we can always choose the one that is best suited for the prevailing circumstances, and probably we can also apply the the ML-based solutions there, so we can optimize, use that to decide on the waveform, use that to optimize certain aspects of the waveform. So I think there are many chances to achieve more universal standard than, for example, 5Gs.
Okay, thanks. Ronnie, I have a few questions regarding OTFS.
Yes.
Okay. The name OTFS implies that it involves space. But
the name OTFS,
what kind of role space play?
Very good. It's a very good question, and the answer to this question is not mathematical. The name OTFS was conceived 12 years ago, before the nature of OTFS was completely clear on the mathematical level, because the OTFS was conceived as part of a company endeavor. So there are few imprecisions. It doesn't account to the true nature of the modulation in many sense. OTFS is a delayed Doppler modulation. You can add to it a space aspect, and in this regard, you can add the S. But OTFS is a delayed Doppler modulation. So I think a better name for OTFS is DDMA, or delayed Doppler multiple access. So that's with regard to the S. I would also say that orthogonal is in a sense wrong attribute of OTFS. In fact, OTFS is a trade-off. OTFS give up on orthogonality. It's not an orthogonal modulation, because all channel distortion in fact destroys orthogonality in delayed Doppler, because you have this high resolution delayed Doppler sensitivity. But OTFS trades orthogonality for predictability and for stationarity. So it's a trade-off that you want to make for specific use cases. So OTFS require a more sophisticated equalizer in order to reap all the benefits. But we now have all the technology, and I think the tip now moved away from orthogonality, which was very important 20 years ago, to predictability, to stationarity, which are very important for machine learning and for other aspects. So that's my remark on this question.
So actually, OTFS is kind of non-orthogonal waveform.
It's a non-orthogonal waveform, and a better way to think about it is delayed Doppler multiple access.
Okay, there's an understanding that OTFS is equivalent to vector of DM. What's your opinion on this?
So in fact, I told the audience what OTFS is. The simplest way to think about OTFS is a pulsar. So this is the carrier waveform. It's a tone sampled over a pulse train. And there are many free parameters here. You can design the spacing of the pulses. You can design there, and another parameter is the shape of the pulse itself, and another parameter is how do you design or how do you shape the full pulse plane. It's a kind of a global filter, local filter, and spacing parameter. There are many ways to interpret this construction. One way to interpret it is a kind of a variant of interleave of OFDM. So you can interpret it in many ways, but all these interpretations are not very revealing. I think the most revealing way to understand OTFS is as a pulse in delayed Doppler, or quasi-periodic pulse in delayed Doppler, related to time by means of the Zach transform. In the same sense that the best way to think about OFDM is as a pulse in frequency related to time by means of the Fourier transform. And why I'm saying it's the most revealing, because when you think about OTFS in this way, you can understand the input-output relation, how the channel interact with an OTFS waveform. That's the most important attribute of OTFS, and the way to understand this attribute and take advantage of it is through the Zach transform and the delayed Doppler structure. So this is the most revealing way to understand OTFS, but you can interpret it as taking building blocks from existing modulation and putting them together in a certain way. You can interpret it like that.
All right. Is pulse shaping still involved in OTFS?
Oh yeah, in fact, large part of OTFS, and we are writing a book now, and there are other existing books on the modulation. I don't think they put emphasis on it. In fact, this delayed Doppler paradigm is a paradigm for the whole theory of signal processing. You can do signal processing on quasi-periodic signals in the delayed Doppler domain. Part of this theory is a filter design. And you design delayed Doppler filters. And delayed Doppler filters are two-dimensional filters, which when you interpret them in time, they are in fact combination of time filters and frequency filters. But the best way to think about them is just delayed Doppler filters. And part of the OTFS paradigm or framework is a filter design. So I can envision how people will come up with filtered OTFS, which means they are not going to use some traditional filters in delayed Doppler. They are going to design filters which optimize certain use cases. So it gives you a complete framework to do the whole signal processing associated with communication transceiver.
Yeah, if we think about filtered OFDM, it's mainly used to reduce out-band power emission to comply with the spectrum mask.
Yeah. You can do the same for OTFS. You can design delayed Doppler filters which create variants of OTFS which abide to some kind of time and frequency constraints.
All right. So the next question is regarding the resource allocation. Can we actually allocate the resource in the delayed Doppler domain instead of time frequency domain?
Yes, there are a lot of work about it. Splitting the delayed Doppler domain and doing multiple access, not using OTFS just as a transmission for a single user, but using OTFS as a multi-user, using the delayed Doppler domain as a control plane. Namely, when actually doing multiple access in the delayed Doppler domain, there are ways to do it, and with guard band, without guard band, and again, for specific situations, there are advantages to doing the multiple access in the time frequency domain. So the answer is yes.
All right, but the allocation of the radio resource in delayed Doppler domain might not be as flexible as in the time frequency domain. Do you agree?
I don't think, there is a lot of research being done on that. It's not, I would phrase your question differently, is not as mature as the multiple access technology on the time frequency domain that was matured over a period of 20 years. So, so you need to give it time. So at this point in time, it's less mature. This aspect of the technology is less mature than the traditional time frequency domain.
Right. Does OTFS also have the high PAPR problem back in OFDM?
Less. OTFS OTFS is a very flexible modulation, and it gives you the freedom to choose its intrinsic parameters so that you can play with the PAPR. You can actually move from a PAPR of a single carrier to a PAPR of a multi-carrier by means of turning the knob of certain OTFS parameters. There is also a variant of OTFS which is called a DFT spread OTFS, which is a kind of a delayed Doppler analog of DFT single carrier of DFT spread OFDM. So there is a delayed Doppler analog of that, which is actually a variant of OTFS, which always have the PAPR of a single carrier.
Right. Okay, last question. I remember on your slide, you mentioned this OTFS for security. Can you elaborate on how physical layer security can be achieved with OTFS?
Okay, I'm not an expert in security. There are a lot of ins and outs in this field, but one aspect of OTFS which I didn't discuss at all for a lack of time is the spread aspect of OTFS. In fact, OTFS fundamentally is a spread spectrum modulation. You can understand spread spectrum in two senses.
Right.
One says in the sense that it actually probes all the diversity passes of the channel. This is easy to understand from the delayed Doppler picture of the channel interaction, but it is also spread spectrum when you use the right filters. It is spread spectrum in the spread spectrum sense. It can create a transmission pattern which looks completely like white noise. And you can actually design these filters. You can actually use the delayed Doppler filters as codes. Every user will have a different filter. There is a coded aspect in these filters, and you can use these filters as a coded signature for users. And in this regard, it gives you a layer of security in the transmission. CDMA is a secure communication kind of modulation. We gave up CDMA, but for a price. So OTFS gives you this attribute of CDMA again. So you regain this coded aspect of CDMA that you gave up when you moved to 4G.
Okay, thanks a lot, Jordan. That's very insightful answers.
Thanks.
Now let's move on to machine learning, Danny. So on your last slide, you showed the bit labeling with the autoencoder. Is this a trained results? And do you need any particular loss function for this?
Yeah, that's a good question. So this is actually a fully trained labeling. So we only basically we only learn in a way a vector of constellation points, and each vector, the index of the vector represents the index of the symbol. And since we are training based on the binary cross entropy, so this will in a way give an incentive to learn in a way this such mapping between the bits and the constellation points that will minimize the bit errors. So it's basically the gray mapping. So you always have one big difference between the adjacent constellation points. So it will learn this basically.
Okay, thanks. Okay, in the machine learning AI community, there's a trend to have a explainable, interpretable AI. But however, the end-to-end learning of physical layers seems to take a black box approach, which is probably against this philosophy. What is your view on this?
Yeah, it is true that this the explainability is an important characteristic that we're actually losing when we are going towards this extremely deep learning. But actually also this the approach that I showed, where we only optimize or learn certain parts of the waveform, is actually bringing some of the explainability back. So it's not a fully black box based optimization, because we can always observe what is the constellation shape, and we can in a way do interpretations based on that. And also I was showing this the convolutional neural network on the transmitter side to deal with the PA nonlinearities. So even that is a rather shallow network. So in a way, my answer to that would be that we need to be really careful what kind of waveforms we are actually learning. So because those are actually going over the air, over the shared wireless spectrum. And then on the receiver side, I think there we have more opportunities because that is purely implementation based. So there, you know, we might be satisfied with some statistical guarantees that you know, with this kind of a data distribution, we will expect to get this kind of a reliability from the receiver side. But it is true that this is still an unsolved problem. You know, how to make these models explainable. And there's a lot of research going on. So yeah, it's an interesting area.
Okay, thanks. If we look at the computer vision, language processing, machine translation, etc., we have we don't have good understanding of the underlying mechanisms of the system. This is where machine learning can play a big part. However, in communication systems, we already have a wealth of expert knowledge. So how can we benefit from this expert knowledge in the end-to-end learning-based approach?
Yeah, that's also an important thing to consider. I would say that there are like a few things that that ML can do, and few things that we can sort of consider here. One of those things is that with ML-based processing, especially on the receiver side, so we have noticed with our own results that we actually can achieve a quite seamless trade-off between computational complexity and performance, detection performance, and this is you know, something that is very easy to do with ML-based approaches. So you can always add one layer, train the model, and you know, you have a little bit higher complexity, but you also get typically a little bit higher performance. And you can also go back in the same way. So in a way, this will allow you to optimize also based on your, you know, power consumption target, for example, or you know, how much power you can use for the inference. And also, I also mentioned this in my intro that these future analog ML chips. So it might even be possible that you will want to do everything with neural networks because they are so power efficient. You can do so many operations within a given power consumption that you can even make some conventional. You can outperform you know, conventional chips and conventional algorithms in terms of power consumption, even if you have a, you know, rather big neural network. So that's also, you know, something to consider, although of course those are, you know, currently only research results, so time will tell if we can really, you know, commercialize that technology. But that's also, you know, something to point out there.
Okay, thank you. So you mentioned that one benefit of machine learning is higher flexibility in hardware, but there's a downside to this, because we will not be able to design efficient and streamlined hardware when using machine learning. How practical do you think it is to use a general purpose GPUs on resource-constrained devices?
Yeah, I would say that we shouldn't use GPUs. GPUs haven't been really optimized for this kind of real-time processing. So I think that with this really specific ML hardware accelerators, so those will be really efficient when we can, you know, really implement these, you know, compute in memory type of approaches. So there, I think that, you know, the current projections are indicating very, you know, high power efficiency there.
The deep learning techniques are data-driven and require training data set. So how is the data set gathered for training? This data set need to be large enough and statistically sufficient to represent the realistic behavior of the channel. Otherwise, the performance of the learning-based approach might not be working properly.
Yeah, I think we are probably running out of time. So yeah, I think this is a very big question. So maybe I don't even try to cover that now since we are running out of time. But yeah, that's something to definitely think about. Yeah.
Okay. So time is up. Okay. Do you have time for one more question? Or?
I think we have 4 minutes. It ends up at 9.
I think it will, the scheduled time to end is 5 to, so at least on my invitation. But
So
yeah.
we need to leave the meeting now.
Okay.
All right. Yeah.
Thank you very much.
Thanks everyone for the fruitful discussion.
Yes.
Yeah,
Right.
thank you.
Thank you. Thank you, Danny. Thank you, Peg.
Yeah,
Thank
bye-bye.
you, the audience.
All right.
Bye.
Have a nice day.
Yes,
Bye-bye.
thanks everyone.
Thank you, everyone.
Mm.